Thanks for coming to our presentation, everybody. My name is Mauricio Villa. For my capstone, I did a smart hard hat. So let's get started. A little bit about me. Last year I wound up in Texas and I was working at a shop called North Texas Manufacturers. I noticed it was really hard to hear our instructions or hear other audio while all of our machines were running. And that was kind of reiterated to me when we were downstairs working in the shop. Cecilia, our assistant instructor, kept having to take her ear protection on and off just to hear what our advisor was telling us to do and all of our instructions. So I thought, how can I eliminate the problem of lack of audio communication while still maintaining that safety of ear protection? And what I wound up with was my smart hard hat. So this is just a little overview of the final product with all the sensors integrated on it. Inside here, we have, on the actual hard hat, we have an embedded microcontroller, which is the particle argon, a simple amplification circuit, and then all the wiring it took to make all the plugs, the audio connections. It's hardwired to the SD card, which is also integrated inside of the hard hat, and just a little button for switching the states. But we'll get into all the more specific stuff here in a minute. The harness which your head actually sits in and snaps into the hard hat only contains neopixels, which are the RGB LEDs to alert you of state changes. It's really just a visual cue for what you're looking at or the environment that you're in. And in the back of the harness, we have bone conduction transducers. So instead of sending your audio through headphones, earphones, or anything like that, it sends it as a sound wave through your bones or really anything that's a non-ferrous metal. And that's really the meat of this project. That's what I'm focusing on, because I thought that was a really neat technology and I really wanted to dive into that and see what application I can get for it. And the sensors I wound up using were the temperature, altitude, pressure, and humidity, MQ9, which is programmable for different types of gas, but for my use, I did LPG, which is liquid petroleum gases, an air quality sensor, and in here, the case ended up closing in on itself. So inside of that is a mini MP3 player, which we'll be using later. So a few of the use cases I came across while using this was construction, and that's what I'm focusing on for this presentation, since I had the hard hat and that seemed the most logical step. Because it's very modular for construction, I'm kind of assuming, since I don't have experience in most of these fields, is gas detection, air quality, and temperature for whatever environment they're working in. For mining, they might want something that's more akin to radiation detection, chaining specified gas sensors so you can get readings of really specific levels of gas instead of one universal gas sensor. And for law enforcement, I feel like they may be more interested in just the transducers so they can keep their ears available while still receiving input. So the sensors, again, we covered are the BME280. Something I didn't mention was the photoresistor. So for those neopixels, since they're LEDs, they're adjustable with their brightness. The photoresistor is really just mounted on the outside, and it kind of just adjusts the brightness of the neopixels for whatever environment you're in. So if you're in a brighter environment, it kind of dims the neopixels a little bit. And if you're in a darker one, it lights them up a little bit more. That little button switches the neopixels back on and off, so they don't always have to be on if you don't want them to. I can understand it's a little distracting. So I really wanted to focus on modularity. That was really important to me for the system. I don't want it confined to just one industry or just one field. And I'm really glad I was able to find these I2C sensors. They chain together to create just an array of whatever sensors you may need. And we'll see how they're mounted on the outside of my helmet later. These are all just MQ9s, but it's a really great example of how they connect and interact with each other. Another connection I have available is the SPI connection. I use that only for my SD data logger, not because I didn't want to use it, but because I didn't really have any other SPI enabled devices that I really wanted to integrate here. And then since our particle argon is Wi-Fi capable, we have connected services both to Adafruit.io, the Particle Cloud, and IFTTT. So really piggybacking off that modularity, we can see those I2C sensors here, really just working in action. So all you do is pull the case off the lid, take it off of the elastic, unplug it, and then you'll be able to swap out whatever sensors you may want for your specific use. That right there, that's being plugged in, I believe it's a color detection sensor, not super important, but it's just in the same family of sensors. So it was nice just to see a little extra something go in there. And it really just shows how much you can do with this. So moving on to my hardware design, the housings I ended up making were modeled in Fusion 360, and we have a Formlabs Form 3 resin printer here at Deep Dive. So I used modeled in 360 and printed in resin, just little modules to clip onto the elastic on the outside. With the section analysis here, oh, did we have a question really quick? I don't. All right. With this section analysis, you can see where the clips are and kind of how they're integrated in a little discrete underneath the cases. These two, the Mini MP3 and the BME 280, they're not super discrete only because they're so small. Relative to the other cases here, you can see how small they are. And even this largest one of the MQ9 is maybe 2 inches by 1.5 inches. So kind of piggybacking off my previous hardware design, I printed in faster printing, cheaper draft resin to make sure the dimensions were correct. And I'm glad I did because they were a bit too narrow for the air quality sensor. And moving on to my circuit design, we can see here the entire module, albeit kind of condensed to a pretty medium-sized breadboard. Something that I didn't mention was that the helmet is self-contained, so it powers itself. You don't need an external power source of any kind except a little battery that sits under the particle argon inside of the helmet. And that battery is maybe about half the size of this one in my schematic. So our audio communication is output through either the mini MP3 player, which you would have to make an MP3 folder for and upload specific audio files, or we have an aux jack in the back that is spliced into the same line as the MP3 underneath this audio circuit here, which you can use as just really any type of aux jack capable device. Here I have it plugged into my phone taking a call, and with the earplugs in, you can still hear the call. Not too sure how good of a resolution the caller would have since it's a noisy environment, but at least you can hear what they're saying. That's really just meant to demonstrate what you can do with this. So the generated MP3 files can be made with any text-to-speech editor. I ended up using Amazon Poly for this, and it let me make these really nice, really clear, high-fidelity messages. We can just demo a few here.
Air quality sensor reading a mid-range value. Be cautious of your environment. All sensors exceeding safe parameters. Please be aware of the dangerous environment you are in.
So we don't have to go through all of them, but I think that's a pretty good example of what's output through the transducers anytime there's a state change in the quality of the environment you're in. And elaborating on that state change, inside of my code, I had 4 different warning message loops, I want to say, just because I didn't want to generate a few dozen MP3s for each little development. So I mapped the parts per million values and to 1 through 4. So there's only 4 different state changes inside of here, and we can see that in this video. Another functionality of this is the SD card logger. If you're not connected to the internet, or for some reason the NeoPixels or transducers aren't working, we have the values of the air quality or the MQ9 or the BME 280, whichever state change ends up happening, and it logs it to an Excel sheet and timestamps it. So right here we can see the state changes just visualized with the NeoPixels. And then the final change would just be the most dangerous reading, which is in red. There we go. So just a more general overview of the usage. As I said earlier, the neopixels are just used to adjust luminosity that's output depending on the environment you're in. So moving from a brighter to a more dark environment, if they were on, they would begin to glow a little brighter. And the button is just used to switch them on and off whenever you'd like. With a little bit of debounce, but that's easily taken care of. And then here I have a can of compressed air, which ended up being a flammable gas. And that is something that's the MQ9 is specifically programmed for. So whenever we output an MP3 message on the surface mount LED inside of the MP3 player, it shines blue. So we can see that there's a warning message going on since the LED is shining. And then our connected services include Adafruit IO, IFTTT, and the particle cloud. And we use that through the particle argon's built-in ESP32. It's just connecting us to Wi-Fi. It's not something that's necessary, but it's a good visualizer, and it really kind of makes that smart aspect of the smart hard hat. So Adafruit IO is, you can create a feed and publish data to it. So here we're publishing the MQ9 readings, the air quality readings, and the temperature readings. I swear it's not that hot in the lab. It's just something I'd set the temperature to so I can get the most extreme value. But my readings aren't very extreme. I don't have many peaks and valleys inside of my data log because they're only mapped from 0 to 4. So the most extreme, I guess, value you'll see here is just a little dip, but it can give you a timestamp of when the data was subscribed. So here with IFTTT, it's another online service that lets us link to Adafruit IO or other online services. I didn't dive too deep into the other services only because I wanted to focus on Adafruit IO. But with the free subscription, you can send out SMS texts to Android phones, or if you have an iPhone, it'll be an app alert. So if there's a state change that you want to monitor, so if it's in a dangerous value above 3 or around 4, then it'll send a text or a app alert to whatever phone you'd like. And I think that would be really good for a supervisor monitoring multiple helmets at once. You can link specific helmets to specific applets and just know who's in the wrong and who's in an area they may not supposed to be in. And the particle cloud was only really used for me for syncing the time. So I didn't really feel like making a timer and trying to extrapolate what time it was when it started or disconnected from the Wi-Fi. So I just connected to particle cloud so I can get that date timestamp. For further development, moving forward in this project, I think I would really like to integrate a GPS module and a microphone for decibel calculation and a transmitter receiver. That's something I was really excited to integrate because that would make using walkie-talkies or other standalone devices really easy. But since I'm working alone, I kind of had to just prioritize which modules I wanted in my product, and the microphone and the transmitter ended up not making the cut. And another thing I wanted to monitor too, since this is standalone, there's not a super easy way to monitor battery levels on this. So I would like to publish something like that to Adafruit IO, and at least, you know, if you're curious about how much charge you have left, you can at least go online and look at it. Another thing I wanted to cover was transducer development. This is a really cool technology in my opinion. It is still relatively new. In essence, it's a 8-ohm speaker. And if that doesn't mean a whole lot to you, just think about vintage headphones. Every time I try to look for a 8-ohm speaker to equate this to, all that's listed online is vintage 1980s headsets, headphones, earplugs. So that's a little bit where this technology is at right now. I think it has a real potential to disrupt markets around audio devices and even further technologies like this. I pulled this quote off of a forum for people that enjoy audio. This Aftershok's Aeropex unit that I've displayed everywhere I've looked, it's described as the best transducer headset that's out right now on the market. And going into that a little bit more, they're not designed for high fidelity playback, so you don't get a great quality out of them. And that kind of just speaks again to the technology that the transducers are at right now. They're more for keeping your ears available while still being able to hear any audio you'd want. But I really would love to get invested in this tech more. So a few of the challenges I came across were calibrating the MQ9. If you can see behind me, I have a big whiteboard of calibrations, and it was a bit hard to figure that out. I had a discrete MQ9 that was way smaller than the one I have now, but the calibration on it was a little difficult, and the I2C one really allowed me to get that modularity with my product, and that's something I really wanted to focus on. So I wound up tossing that discrete and using the larger I2C one. Another challenge was that prioritization of which sensors to use and which to leave behind. I don't really want to say leaving behind anymore. I want to say put for further development, because they are definitely things I would want to integrate later on in this. And making this customizable and making it a good configuration. I had intended to mount all of the sensors inside of the helmet and cut holes in the helmet, but that ended up getting really clustered and not working too well. And mounting them on the outside allows for any configuration that a user may want, and it's just easy to plug them in. Efficiently wiring the helmet, since this is intended for safety, there are certain parameters I kind of wanted to follow. I know this isn't a production ready product, but I still wanted to have some clearage between the harness and the hard hat, so in case anything fell on it, that it would impact the hard hat and not your head. And I got around that by just mounting everything on the outside, and the only integrated parts were the really small ones, like the SD card logger, the photoresistor, and then the amplification circuit and particle, which are all pretty discrete for this. And since these sensors return values in parts per million, getting a very low range and getting a very high range to figure out the map I needed to use was a little bit difficult, only because it was kind of hard to simulate some of this LPG and some of the air quality sensor high readings. I ended up using isopropyl alcohol and that compressed air, and that ended up working great. But other than that, testing all of it went pretty well. I think it works very well, but yeah, that's my product.